So we talked about fluid storage in conventional and unconventional resources in topic 2. Now in topic 3, we'll be talking about fluid transport in conventional and unconventional resources. So we talked about flow capacity and storage capacity. In topic 2, we focused on storage capacity. Now we are focusing on flow capacity, which is a product of thickness and permeability. Right, that's what is given here. So if you are given the thickness of a reservoir, the only petrophysical parameter you need to get the flow capacity is permeability. So it will control fluid flow in a reservoir rock. And I mentioned at the beginning of topic 2 that porosity and permeability are the most important petrophysical properties. Porosity will indicate the volume of the petroleum stored in the rock, whereas permeability will indicate how quickly you can produce it. So it indicates the rate of flow. The amount of fluid stored is what you get from porosity. The rate at which you can produce it is what you get from the permeability, basically. Permeability, by definition, is the measure of the ability of a rock to transmit fluids. So it is a rock property. It's measured in units of length squared. So in SI unit, that will be meter squared. But in field units, it's Darcy. And this is a picture of Henry Darcy. And he performed experiments that led to the Darcy's law. When you read his biography, you will see he wasn't a petroleum engineer. He actually showed up before the petroleum industry. And his focus was on water filtration. So his motivation was to improve the quality of drinking water supply. But we have used his equations in modeling fluid flow in petroleum reservoirs. It's one of the most fundamental equations used in all of reservoir engineering. So this is a sketch that is close enough to what his initial setup was. He had a sand bed, which is what is shown here. So this is sand. And then he measures the length of the sand bed, right? And then he puts the water to be filtered on top of the sand bed, and then the water slowly seeps through the sand at a fixed rate, and that rate is Q. So in addition to the length, he knows the area, the cross-sectional area of the sand bed. And then the pressure of the fluid upstream of the sand bed and the pressure of the filtered water downstream of the sand bed is indicated by the pressure head. So this is the head upstream and this is the head downstream. And using all those parameters I just highlighted, he was able to calculate permeability from flow rate. So what he observed fundamentally was that there was a relationship between the rate of fluid flow coming out on the downstream of the sand bed. That flow rate is proportional to the difference in the head, indicating difference in potential or pressure. And then he divides that by the length of the sand bed, right? And then multiplies by area. So flow rate is proportional to area, I should say. Flow rate is directly proportional to the area of the sand bed, but it's inversely proportional to the length of the sand bed, and it is directly proportional to the difference in pressure head. And then the constant of proportionality is referred to as the permeability. So you can write this equation in this form. difference in pressure head, and then we'll multiply the K by the area here. And that's the form of the equation we use, except instead of heads, we work with flow potential or pressure when the flow is horizontal. So today, our measurements of permeability look more like this. So instead of flowing through the sand bed in the vertical direction, we actually flow horizontally. And then the permeameter, which is the name of the equipment, is able to show you pressure difference between the upstream and downstream. So this will be the upstream, and this will be the downstream. So the equipment actually displays that pressure difference between the upstream and downstream, and then you're able to measure the flow rate. So it records the rate of flow of fluid through the sample, and then we measure the dimensions of the sample in terms of length and cross-sectional area. So we have this expression. Only thing we've introduced is viscosity, because you can flow fluids different from water. And you know the reason viscosity doesn't show up in the original Darcy equation is because the viscosity for water is approximately 1. But if you use a different fluid, the viscosity could be greater or less than 1, and so you have to divide by mu, because flow rate is inversely proportional to the viscosity of the fluid you're flowing through the porous medium. This V is Darcy velocity, and it's basically the flow rate divided by the cross-sectional area. And the reason we call it Darcy velocity is because it's different from what is called the interstitial velocity, which is actually the velocity of the fluid moving through the tortuous porous medium. So moving through the tortuous path, which is basically the interstices of the porous medium. So that's why it's called interstitial velocity. So the velocity of the actual fluid through this tortuous path is going to be faster than the velocity it will take for the fluid at this point to get to this point, because this length is actually shorter than this tortuous length. So this physical length is L, and then the length of the actual path the fluid takes to go from one point to the other is the actual length, which is the length of the interstices. And that's why this interstitial velocity is typically of a bigger magnitude than the Darcy velocity. And you can calculate it from the Darcy velocity by simply dividing by porosity, which will be less than 1, right? So you can see even in the definition that the interstitial velocity is typically faster than the Darcy velocity. But the Darcy velocity is the one to be used here. So Q over A equals velocity. So the expression for velocity will involve dividing both sides by A, right? So that gets you V here. And then when you divide this by area, the area goes, and you're left with K delta P divided by mu L. And the negative sign is to account for the fact that fluid flows from upstream to the downstream. Fluid doesn't flow uphill, basically. So you can make the calculation without the negative sign, and then you figure out the direction of flow by the fact that fluid will go from the higher potential to the lower potential. These are some of the assumptions in Darcy's law. It assumes laminar flow. It assumes no mechanical deformation of the porous medium, so no geomechanics. It assumes the porous medium is homogeneous and isotropic, but you will see it can easily be extended for the anisotropic case, right, where the permeability could be different in different directions. And then it assumes you have single phase flow and that the rock is fully saturated. but it has also been extended to multi-phase flow using the concept of relative permeability. It assumes the pressure gradient is constant and that the fluid flowing through the rock is a Newtonian fluid.